Today's lecture is going to be recorded, and the first part is Laplace transform of derivatives. So if I want to find the Laplace transform of the derivative of a function, then what I need to do is to multiply by s the Laplace transform of the function itself and subtract the value of the function at 0. That's the most important thing about that. Some people like to write the formula for the n derivative, but I say that's a waste of time, because once you have this formula, you can find the Laplace transform of any other derivative, second, third, fourth, using this consecutively, right? So as example on this, you can have the Laplace transform of the second derivative as an example. That will be applying this formula. The second derivative is the derivative of the derivative. So this is S, Laplace transform of the derivative, minus the value of the derivative at 0. And the Laplace transform of f prime, again, you use that, you get that it's s squared, s times s, Laplace transform of f minus f of 0, minus f prime of 0. So you can open those parentheses and see that the Laplace transform of the second derivative is s squared Laplace transform of f minus f s f of 0 minus f prime of 0, and so on. You can find Laplace transform of the third derivative, Laplace transform of the fourth derivative, continuing the same way. Laplace transform of the third derivative. You tell me here, how would I find the Laplace transform of the third derivative? Applying this formula. Did you help, Joel? I want to apply this formula on that function. How would I write that down?
Would it be s times the Laplace transform of the second derivative minus s first
I
derivative
can't
0?
hear anything.
Can you hear me?
I can hear you.
Mrs. Jones, can you say something there? I don't know. It seems I can't hear any.
He's talking, or he was.
Can you hear me?
Yeah, I can't hear you either. That's S. So here, the third derivative is the derivative of the second derivative. So that's S Laplace transform of the second derivative minus the value of the second derivative at 0. Value of the function that is in here at 0. Value of the function that is in here at 0. Value of the function that is in here at 0. And the Laplace transform of second derivative is found above. So that's S squared Laplace transform of f minus S f of 0 minus f prime of 0 minus second derivative at 0. And you can do that as much as you need, depending on the problem that you have to solve. Okay. I can say Laplace transform of cosine of t is S Laplace transform of sine t minus sine of 0, because cosine t is the derivative of sine t. Applying that formula, the Laplace transform of cosine t will be S Laplace transform of sine t minus sine of 0, and sine of 0 is 0. So that's S Laplace transform of sine t, and you do know that this is true because the Laplace transform of cosine t is S over S squared plus 1, and the Laplace transform of sine t is 1 over S squared plus 1. That's just to show you on this example that you already know that it's actually what it is. Now, these are things that are used in applications to find the solution of a linear differential equation or an integral differential equation. So now let's part B. Here is the convolution. Convolutions and convolution theorem. So this is the part where, after covering this topic, we have the most mistakes from students because we start looking at the function. When you ask for Laplace transform, we just multiply answers without knowing that technically what the theorem says is only about convolutions, not about products of functions. So the definition of a convolution is the convolution of f and g is f star g of t equals integral from 0 to t f of tau g of t minus tau d tau. So this is the operation that we call convolution of g and t and f. And it doesn't matter that we say f and g or g of f, because this operation is actually commutative. So no matter which one you put first and you compute, you are going to get the same answer. So g f star g and g star f are equal, and both equal to the integral from 0 to t of f of tau g of t minus tau d tau. And as example, you can have that 1 star f of t for any function f of t is integral from 0 to t. 1 at tau is 1, g of t minus tau d tau, which is here for f, sorry. And this is also equal to f of t star 1, which is integral 0 to t f of tau d tau. Any questions? So if in a problem you see integral that, you know that it's f of t star 1 or 1 star f of t, and if you see that integral, it's the same thing, right? Sine of t star 1, it's integral 0 to t sine of tau d tau, and you integrate sine of tau. In this case, you get negative cosine of tau, plug in 0 and t, so you get 1 minus cosine of t. So that is sine t star 1, right? If I say t star cosine t, that's going to be integral 0 to t, f is tau, cosine t minus tau d tau. And we can integrate this by parts. So if this is u and this is v prime, and then u prime is 1, v is negative sine of t minus tau. So you get negative tau sine of t minus tau 0 t minus integral 0 to t, and then 1 and minus sine of t minus tau d tau, and that's equal, when you plug in t here, when you plug in 0, you get 0, when you plug in t, you get negative t, and sine of t minus t is 0, so when you plug in t and tau here, you get 0 for both. Minus and minus, that becomes plus. The integral of sine of t minus tau is cosine of t minus tau, and you plug in 0 and t again. When you plug in t minus t is 0, cosine 0, 1 minus when you plug in 0, what we get here, t Yeah, cosine t. You can see that here we got the same result I would have there, though the functions are very different from those. Any questions? Right now, right from this one is what we call the convolution theorem, which states that the Laplace transform of f star g is equal to the Laplace transform of f multiplied by the Laplace transform of g. And that's the only place in this course where the Laplace transform turns into the product of the Laplace transforms, because here you have convolution, which is defined here. It's not a product here. That being said, it can be used to answer the other part of the topic of the day, which says Laplace transform of an integral. And that's the reason why I gave you right here the example of 1 star f of t and f of t star 1, because this is technically the integral of f of t. And the integral of f of t, this says, is f of t star 1. So Laplace transform of integral 0 to t f of tau d tau is equal to Laplace transform of f of t star 1, which is Laplace transform of f multiplied by Laplace transform of 1, which is 1 over s Laplace transform of f of t. So if I want to find the Laplace transform of the integral of a function, it's just 1 over s times the Laplace transform of the function. Any questions? So this thing is used in two directions, actually, that theorem, as any other of the theorems that we have in this chapter. It's used forward to find Laplace transform of this, and it's also used backwards to find the inverse Laplace transform when you see that capital F of S is written as a product of two functions that you know the inverse Laplace transform of. You can just say, hey, it's equal to the convolution of the two functions, and then you can compute the convolution. Let me show you an example. So, example 2, find inverse Laplace transform of 1 over s minus 2 times s plus 3. Before we got to this section in this class, if I ask you to find this inverse Laplace transform, what you would do would be do partial fractions, find the partial fractions, and find the inverse of each of them. But after this topic, when you look at this question, you say, okay, let me use a more advanced tool. So I would say inverse Laplace transform of 1 over s minus 2 times s plus 3 equals the inverse Laplace transform of, and this here is Laplace transform of e to the 2t times Laplace transform of e to minus 3t. Because 1 over s minus 2 is Laplace transform of e to the 2t, 1 over s plus 3 is Laplace transform of e to minus 3t. And because it's the product of Laplace transform, the inverse Laplace transform of the product of Laplace transform is equal to the convolution of the two functions that you have there. And that is a direct application of this theorem, which states that the Laplace transform of the convolution is equal to the product of Laplace transforms, which means that the inverse Laplace transform of this is the convolution. Yeah. And so when I write this way, I just go ahead and I write that that's the answer. Like this is integral 0 to t e to the 2 tau times e to the minus 3 times t minus tau d tau, because it is f of t times g of t minus tau. And now we can do the computation integral 0 to t. We combine those things. This is e to negative 3t plus 5 tau d tau, because this is negative 3t plus 3 tau plus 2 tau. That's it. And when you integrate that, it's e to negative 3t plus 5 tau, 1 over 5, and you're integrating 0 to t, so you plug in t, you get 5t plus 3t, 2t, so that is 1/5 e to the 2t, and then you plug in 0, you get minus 1/5 e to the minus 3t, and that's the answer. And that's the same answer you would get if you did first partial fractions. Any questions on this? Okay, so if no questions, then please do this exercise. Find Laplace transform of t squared star t e to the 2t. Does anyone have something to share? First step. Applying the theorem. This is the convolution. So that is Laplace transform of t squared times Laplace transform of t e to the 2t. Laplace transform of t squared, that's 2 over s cubed. Laplace transform of t e to the 2t. Sorry, but here I cannot multiply and say it's Laplace transform of t times Laplace transform of e to 2t because this is not a convolution. So you need to be very careful with that. That's where the mistakes begin. This is not a convolution. This is t times e to the 2t. So the Laplace transform here needs to use all the rules that we've been through. It is t e to the 2t. So you can use either Laplace transform of derivatives or derivative of Laplace transform, or because of e to the 2t, you can use first translation theorem. So it's one of the two things. So here it's going to be, I use the translation theorem. Laplace transform of t is 1 over s squared, and I replace s by s minus 2. That's using first translation theorem. Someone else could use derivative of Laplace transform and still get the same answer. And so when I do that, that gives me 2 over s cubed times s minus 2 squared. That's it. If we say find the Laplace transform of integral 0 to t e to negative tau cosine of tau d tau, and then you can see that this is a Laplace transform of the integral. So this is a Laplace transform of cosine t e to negative t star 1, which is 1 over s Laplace transform of cosine t e to minus t. That's the first step. And now you continue again here. Because of e to the minus t, I need to use a translation. So that's 1 over s, and this is no more convolution. I need to use first translation theorem on that one to finish. And that's why I was saying you need to practice before getting to this lecture, because it takes into account all other topics that were done before. And if you didn't practice any of them, then all this I'm doing now would be a waste of time for you. So after the first step, you head on this, which is use 7.123, and that one here is first translation theorem. So I'm gonna do Laplace transform of cosine t, and then I'm going to shift and replace s by s plus 1. Why s plus 1? Because it's e to minus t. And then that is 1 over s times, and the Laplace transform of cosine t is s, and I replace s in that by s plus 1 over s plus 1 squared plus 1. That's it. So the answer to that question will be s plus 1 over s times s plus 1 squared plus 1. And notice that I computed that without ever computing the integral, right? And the question says, most of the time, find the inverse Laplace transform without computing the integral to force you to use the convolution theorem. The other one next to this is find the Laplace transform of tau e to the t minus tau. In this one, you can see right away the formula of the convolution. For the formula of the convolution, you need to see one function of tau and you need to see the other function of t minus tau. The function of tau here is just tau, so that's t. And the function of t minus tau is e to the t minus tau, which is that. So this function here, so this integral, right, 0 to t. So Laplace transform of the integral from 0 to t of tau e to the t minus tau. And so this is Laplace transform of t times Laplace transform of e to the t. And here, each of them is simple. Laplace transform of t is 1 over s squared. Laplace transform of e to the t is 1 over s minus 1. So that's 1 over s squared times s minus 1. Any questions? So the main thing to keep in mind here is that after identifying that you have to do with the Laplace transform of a convolution, you need to see that the next step might involve something else other than the convolution, either the first translation theorem, sometimes the second translation theorem, sometimes Laplace transform of derivatives, and so on. So let me get you to think about this one. So solve the equation, second derivative minus twice the derivative equals t e to the t, where y of 0 equal y prime of 0 equals 0. That uses the first topic we had today, Laplace transform of derivatives, and it will use also the inverse. So the first thing you do here is apply the Laplace transform on the whole equation and find the Laplace transform of y, and then find the inverse of it. Those are the steps. And technically in this class at this point, you can do all of that and do this you are done with this course. Everything else that comes after this is just repeating and repeating and repeating the problems. There is nothing new that is going to show up. So all we have to do now is to apply these to different problems and have problems where they will all be combined. That's it. To start answering this question, you start by setting that the Laplace transform of y, we will call it capital Y. So we find Laplace transform of y prime. This is S Laplace transform of y minus y of 0. Y of 0 is given here 0. So that's S capital Y of S. Laplace transform of second derivative, that is S, Laplace transform of the derivative minus the value of the derivative at 0. And again, the value of the derivative is 0, so that's S squared capital Y. So the whole equation and the Laplace transform of t e to the t is 1 over S minus 1 squared. So we replace all of that in the equation. So we are going to have second derivative, Laplace transform of second derivative, that's S squared capital Y of S minus 2 Laplace transform of Y prime, that's S capital Y of S equals Laplace transform of t e to the t, which is 1 over S minus 1 squared. So that's what the equation turns into, which you can solve for capital Y of S equals 1 over S squared minus 2S times S minus 1 squared. So this is the Laplace transform of the solution of this problem. And now to finish the solution, what we need to do is to find the inverse Laplace transform to find y of t. That's the last step. Find the inverse Laplace transform. And that's the reason why, like I said, those things are connected. Once you start, you do all the things that we did today, and you end up having to apply 7.123 to finish the problem, to find the inverse Laplace transform. So how do we finish the job here? I would say this y of s, which is 1 over s minus s squared minus 2s times s minus 1 squared is equal. We can solve this problem using partial fractions. That's the easiest one here. So we can say it's a over s plus b over s minus 2 plus c over s minus 1 squared plus d over s minus 1. And then we find a, b, c, d. And so that is going to tell us that 1 is equal to a s minus 2 times s minus 1 squared plus b s minus 1 squared plus cs plus d s times s minus 1. And now, as we did last time, we plug in the numbers. If we plug in s equals 0, we get here 1 equals, and here it's minus 2a. So right away, we get ready a equal negative 1/2. If we plug in s equal 1, we get 1 on the left equal 0, 0, 0, c. So right away, c equal 1. If we plug in s equal 2, on the left, we still have 1 equals on the right, 0. We're missing something here. I'm missing s minus 2 here. And we are missing s minus 2 here. All right, and if that's the case, for A, it's okay. For C, you get 1, and then 0, 0, and here, minus 2c. So C is minus 1/2. So that's s minus 2. Now s equal 2, you can see it right away when I wanted to plug in this, I see there is a mistake because I have more than one term that is not turning to 0. So right away you see there is a mistake. And you go back and fix that. So here, again, we go, that's 1. And then here when we plug in 2, that's 0. And here we got 2b, because 2 minus 1 is 1. 1 squared is 1, 2b. And here 2 minus 2, 0, and 0. So you get b equal 1/2. In these problems, usually you must just get one number right away from each of the numbers that you plug in. that turn other terms to 0. Now we got all numbers except D, so we can choose to plug in anything we want to get D. So I plug in S equal -1. So I'm gonna get 1 equal S equal -1. So this is -3. Here -2 squared, that is 4. So that's 4 times -3, so -12a. And a is -1/2, so that's +6. And then you get to b, s -1, that's squared, so that's 4 -1, so -4 times 1/2, so that's -2. And then you get c, s again, -1, so that's -3, -3 times -1, so that is 3. Three times c, which is -1/2, so that's -3/2. And then -1 times -2, so that is 2 times -3. That's -6, and d, so -6d. And now you can do the algebra. So that is like 3 -3/2 -6d, 0. 3 -3/2 is 3/2. So d is 1/4. And so you would have little y of t. And sometimes I even ask students, after writing this down, if you can't get those coefficients, perhaps go ahead and find the inverse Laplace transform of what you have there. So this is going to be a inverse Laplace transform of 1 over s is 1, plus b inverse Laplace transform of 1 over s minus 2 is e to the 2t, plus c, and the other one is t e to the t, for 1 over s minus 1 squared, and the other one d e to the t. That's what your answer is, even if you don't know a, b, c, d. You can still get that. And now if I have them, I plug them in, the -1/2 plus 1/2 e to the 2t minus 1/2 t e to the t plus 1/4 e to the t. So that's the answer. Any questions? Time is over. If there is no question, you feel free to go. If you have a question, you can stay to ask.
Thank you for emailing me back this weekend. I was had to go up to Memphis, and so I ended up coming back home and doing my